Hello, my name is Jenny Madsen from Team Integral and ME223 Design. Our team consists of Diego Juarez, Zach Howard, Quaid Murray, and myself. This video is the conclusion of our design project, which we were asked to design a bicycle lift system capable of increasing free floor space in a garage and overall safety by lifting and suspending a bicycle using a DC motor and simple machines. Our group was challenged to create a kit which can be marketed as an education aid to our consumer segments that consist of professors and their students. Essentially, our kit is a quick and dirty, hands-on engineering project in a box. Our explanations throughout the video are aimed at product delivery to our expected consumers. Every successful item on the market depends on appealing to 5 drives relative to human behavior. This bike lift project is simple and useful as a teaching aid for professors and will be sought after by students wishing to pursue hands-on application projects. Our kit will promote group learning, bonding, networking among peers, and will be a talking point among professors experienced with our project. Professors will learn alongside students using this awesome, new, hands-on DIY approach at teaching fundamentals. Time is vital. Luckily, our kit reduces prep time while maintaining quality-level project standards. Students will be secure with a level of recall inherent in hands-on training and their ability to get things done fast in the future, as well as the quality experience and resume material that will be gathered. This project will be an excellent experience for all users, inspiring competency, setting the example for future-based project work. This kit would include an ARDX starter kit, pulleys, string, and all necessary components for a quick startup. A link to a short informational video would be provided with an intro to key concepts that would help prime students and teachers. As I present a few key concepts relevant to the bike lift project, my intention is to introduce a discovery-based method of tackling the more complex concept of efficiency. Concept 1 is on mechanical properties. Engineers begin by focusing on objects that aren't moving for simplicity by stating that in a system forces are equal and opposite and can be equated to one another. We call this summing forces and moments. Newton's second law of motion states that force equals mass times acceleration often being our gravitational constant of 9.81 meters per second. Torque, or a moment, is relevant to our data and is equivalent to force applied perpendicular to the distance away from the given center point that we choose. Students will be required to learn basic C++ programming and electrical circuit construction with Arduino. Success with electrical concepts is dependent on knowing Ohm's law, where voltage in volts equals the current in amps multiplied by resistance in ohms. You will also want to study DC motor basics, where electromagnetism is used to create mechanical power. Efficiency relevant to our lift data is dependent on mechanical power going in and electrical power coming out. Mechanical power equals work divided by time and is expressed as joules per second. Work is equivalent to force times distance. Electrical power is a function of current multiplied by voltage. Your voltage will be equivalent to power source in a simple circuit. The current can be fixed or variable and shall be adjusted with the potentiometer in this laboratory. Now we have enough information to derive our efficiency equation. Efficiency is a function of mechanical power in divided by electrical power going out. So force multiplied by distance divided by time, our mechanical power, can then be divided by voltage times current, our electrical power out. Mechanical advantage can be accounted for in the force used in our work value. For a working example, we created a lift design using the supplied Arduino kit, an easily replicated belt system, and a team cooked up concept for angular elevation. For mechanical advantage, we see a 1:6 ratio in our belt drive. Our angular lift reduces force due to gravity by the product of sine theta as a function of time through the lift sequence. The motor drives a belt system, used to uptake a cable driven under a pulley, then hooked to the end of a moment arm, which our bicycle is attached to with hooks. As current is supplied to the motor, the rear tire takes a 90-degree semicircle path upward until the bike is positioned vertically against the wall. This inverted wall position takes less energy to obtain and creates a very small footprint on the wall. The bike lift might seem complicated, but it's simple to run. You get to control the motor using pulse width modulation, controlled through a potentiometer. Unfortunately, you can't just raise and lower your lift with a snap. We solved this issue by programming a relay with 2 buttons to reverse the current and direction of our motor's revolution. But there are lots of different solutions to this problem. Belts are so easy to make and perform equations on, we couldn't help ourselves. We used belts and angular lift to our mechanical advantage, garnering about a 20% increase in power efficiency, bringing our total efficiency to a whopping 26%, which is pretty good for motors. For system specifications, we used a 130 size DC toy motor and a 5-volt power source. We lifted a total mass of 0.6 newtons in 3 seconds. Our bike was lifted 15 centimeters based on change in the center of gravity on the bike. In our load testing, we found a 10-gram mass to use 1.3 volts of charge while drawing 90 milliamps of current. Our efficiency was figured at 26%, as was mentioned before. As future engineers, we're held to rigorous standards by mentors and peers. We constantly seek methods to simplify our day-to-day skills. Life skills such as critical thinking, effective communication, and reflective thinking are valuable go-to skills which are extremely simple and useful to engineers. When applied, these skills perpetuate good organization, camaraderie, and unsurpassed problem-solving technique inherent in the best of engineering practices. Is there a better way to get our job done? Critical thinking is a technique for solving problems based on applying oneself to a job using what you know, gathering information from available sources, and seeking outside help from knowledgeable people. Put simply, through listening, observation, writing down our ideas, and fully applying ourselves so we can see success in very short amounts of time. The next key life skill is reflective thinking. We might reflect on what went well during a project. Then, what could have been improved during the project? Mental and physical notes are made of this time and these ideas. Plans for future adjustment are made and, more importantly, acted upon, creating a simple self-accountability program. Try it in your teams, you guys. Critical thinking is a technique for solving problems based on applying oneself to a job using what you know, gathering information from available sources, and seeking outside help from knowledgeable people. Put simply, through listening, observation, writing down our ideas, and fully applying ourselves so we can see success in very short amounts of time. Speaking of getting stuff done, my time's about up. Thanks for listening. We hope you've learned some basic mechanics and hope this has helped you for your plan for future lift ideas in your own or your students' futures. Best of luck with your bike lift projects. Thank you.